This video, this screencast lesson, is to review what happens to cells when they're placed in various solutions, such as isotonic, hypertonic, and hypotonic solutions. So I got a little bit of a head start here. I made a very terrible drawing of a solution that happens to be isotonic, and I've already placed a cell in the solution. Now keep in mind that isotonic solution means that there's a tiny bit of solute, as you can see here, and all these drawings are going to represent the solute, the thing that's been dissolved, with these red dots. So these will be our solutes, and it just so happens that in this case the solvent is water. So we'll write a couple of H2Os in there to represent the solvent. As we've noted before, water is the universal solvent. It is very often the solvent in a solution. Hard to come up with examples where it's not. Now, keep in mind, again, that osmosis, which is what we're going to be talking about here, primarily, the movement of water across a cell membrane. So it's water across a membrane due to diffusion is called osmosis. So the water is moving due to diffusion, but it's such a special process that when water diffuses across a cell membrane, in either direction, by the way, into or out of a cell, we call it osmosis, okay? Now, how does diffusion work? Well, as mentioned before, everything diffuses due to the concentration gradient. So that's your rule. So if you can determine where there is a higher concentration of particles, substances, solvent or solute, then you can determine which direction something might be moving due to diffusion. So if there are lots of particles here, we would call this a high concentration of particles. And due to particle theory of matter, we know that they'd be moving around, they'd be bumping into each other. And if there was a container here, they would just stay in this container, say acting like a liquid, perhaps. But if the barrier was removed, they would very quickly spread out, bump into each other, and fill the remainder of the container until they were pretty much evenly spread out throughout the container. So they would move from area of high, from area of high to low concentration. So that is what we call the concentration gradient. And it drives all of the diffusion that happens in, not just, I was going to say living things, but all diffusion is driven by the concentration gradient, okay? So what's happening in this solution? Now, cells, I've already labeled it. A cell is isotonic. So cells have a good bit of water in them. We'll try to scooch a water molecule in there. And they do have things dissolved in them. But we call that situation isotonic. So iso does kind of mean same or equal to, but in a living system, isotonic means that there's probably about 20 to 30% of the solution there's a solute, a thing that's dissolved, and then the rest of it is the solvent. And in living situations, living things, the solvent's always water. So let's look for a concentration gradient. We've got a few bits of solute in the solution. There's bits of solvent. I'm sorry, I should have said I said solute. Solute in the cell, and there's also solvent outside of the cell, solvent inside of the cell. So therefore, there's no actual concentration gradient. So in an isotonic solution, a cell will not change. So there's no change in a cell placed in isotonic solution. That's really good news for those of us who've ever been on an IV drip. Typically, that was saline solution, and saline solution is isotonic. It's used to replace a lack of fluid to hopefully make us feel better if something's not going well. All right, let's talk about a hypertonic solution. So here we go, new solution. Still has water as the solvent, and there's a fair number of water molecules in there. If not, it probably wouldn't be much of a solution. And it's got a whole load of solute. Doesn't really matter what the solute is. Could be salt, could be sugar, could be some other mineral, but there's a lot of stuff dissolved in here. So therefore we classify this as a hyper, over the top, lots of hypertonic solution. So what's going to happen if we put a cell in here? Let's carve out a little space, put in our cell. So here comes our cell, and again, what's our cell? The cells are isotonic, okay? So just a couple little, there's a fair number of solute in there, a pretty good amount of solvent. But the key thing to know, since it's hypertonic, there's a huge amount of solute outside of the cell, which decreases, relatively speaking, decreases the amount of solvent. And the thing that's going to be doing the moving here is the water. Water can easily cross the cell membrane. These molecules might not be able to, so the water is going to move where? Out of the cell, right? So since there's a high concentration of particles, solute outside of the particle, lots of solute, decreased solvent, throw an L in there, there's an L somewhere, decreased amount of solvent compared to the cell, the water is going to leave the cell. So the water is going to leave, and therefore the cell in the hypertonic solution is going to decrease in mass, aka it's going to shrink. It's going to be losing all that water, okay? We've mentioned a couple examples of that. That's why you never want to drink, a large amount of ocean water, for instance. Ocean water is fairly highly saline, meaning it's got a lot of salt dissolved in it. So over time, that would be very bad for our human system. Final situation is, what about a solution that's hypotonic? Now, hypo means under, right? Hypo, under, below, less than, I think, something like that, hypotonic. So this is going to be pretty much pure solvent. So in this case, lots and lots and lots and lots of water. Let's get our cell in there. There are still a few bits of solute. You can almost never make a purely hypotonic solution. There's some solute in there. Don't forget now, our cell is isotonic. So the cell has some water, some solute, right? But outside of it is this huge amount of water, huge amount of solvent. So what's going to happen in this case, the cell is actually somewhat, let's say, salty compared to the solution. The solution is mostly water. Again, following the concentration gradient, there's a higher amount of water outside the cell than inside the isotonic cell. So water is going to go into the cell, which is going to lead to this cell increasing in mass, greatly blowing up. And if it stayed in there for a very long period of time, the cell would eventually burst. There's so much water would diffuse into the cell via osmosis that it would eventually burst. Okay, that's our review of hypertonic, and isotonic solutions and what would happen to the cell in each one of those situations.